Welcome back to the series. This is Stage 5, Lesson 36, and today we're going deep on NAT and PAT. These two technologies are the quiet reason your home network, with its handful of private addresses, can still reach anywhere on the public internet. Over the next few slides, we'll unpack how a clever stopgap from the mid-90s became permanent infrastructure that's still buying us time before full IPv6 adoption. Here's the path we'll take. First, the origin story, why NAT had to exist at all, and how IPv4 exhaustion forced the issue. Then we'll break down the three working flavors: static NAT, dynamic NAT, and PAT, which is the one quietly running in your router right now. From there, we'll get practical with port forwarding and NAT traversal, and finally, we'll confront the awkward question. In an IPv6 world, does NAT still deserve a seat at the table? So let's start with the origin story. IPv4 gives us roughly 4.3 billion addresses, a number that sounded generous in the early 80s, but today has to stretch across 8 billion humans and over 30 billion connected devices. IANA actually handed out the last public IPv4 blocks back in February 2011. The fix, proposed in RFC 1631 in 1994, was elegant, mapped many private addresses behind a single public one, multiplexing up to 535 flows per IP using port numbers. It was meant as a stopgap until IPv6 matured, and 3 decades later, it's still holding the internet together. Before we go any further, we need to untangle Cisco's NAT vocabulary, because a single packet actually carries 4 different names, depending on who's looking at it. Break it down on 2 axes. Inside versus outside tells you which side of the NAT boundary the host lives on, and local versus global tells you which IP you'd see from that vantage point. Private on the local side, public on the global side. So your laptop at 192.1168.110 is the inside local address. The public IP and port it gets translated to, say 203. or 3.5, port 5431, is the inside global. The destination, Google at 142.250.1187.46, is the outside global. And in simple NAT, it looks identical from the inside, making it the outside local too. That last pair only diverges in twice NAT, which we'll save for later. With the vocabulary settled, NAT itself comes in 3 flavors, each answering a different question. Static NAT is a permanent one-to-one map, perfect for a public web server that needs a stable, reachable address, but it burns a public IP per host. Dynamic NAT hands out addresses from a pool on a first-come, first-served basis, useful when you have fewer public IPs than internal hosts, though each mapping is still one-to-one, so a busy network drains the pool fast. And then there's PAT, or NAT overload, the one running on virtually every home router. Many private hosts share a single public IP, distinguished only by source port. That's the trick that actually bought IPv4 another 2 decades. Look at the translation table and the trick becomes obvious. Every internal host, 10, 11, 12, all the way to 14, appears on the outside as the same public address, 203.113.5, but with a different source port stitched on, 6001, 6002, 6003, and so on. Notice that point 10 even has 2 simultaneous flows of its own, distinguished only by the original port. When a reply comes back to 203 13.5 6003, the router consults this table, finds the matching row, and forwards it to 192.168.1.11 on port 5001. One public IP, dozens of conversations, no ambiguity. Now let's see how you actually tell a Cisco router to do this. Every flavor starts the same way. Tag one interface as IPNAT inside, the other as IPNAT outside. The router has to know which direction it's translating. From there, you pick your model. Static NAT is a single line mapping one inside address to one outside address, permanent and predictable. Dynamic NAT adds a pool of public addresses and an access list that decides who's allowed to draw from it. And PAT, the one you'll deploy 99 times out of 100, is almost identical to dynamic, except you skip the pool, point at the outside interface, and add the keyword overload. That single word is what enables the port multiplexing we just watched in the translation table. There's a catch with PAT, though. By design, it only works outbound. A connection initiated from the outside has nothing in the translation table to match, so the router drops it. That's fine for browsing, but useless if you actually want to host something. A web server, a game server, an IP camera. Port forwarding fixes that with a static rule. Any traffic hitting the router's public address on port 443 gets redirected to 192.168.1.10 on port 443. You can fan multiple services off one public IP or even remap ports, 8080 outside landing on 80 inside. And yes, UPnP will create these rules automatically, which is convenient right up until you realize any application on your network can punch its own hole through your firewall. But port forwarding only helps when you control the router. What about Zoom calls, online games, or VoIP soft phones running on millions of networks the developer has never seen? That's where NAT traversal comes in. Stun is the simplest trick. A public server tells your client what its translated address actually looks like from the outside, so it can hand that to a peer. When stun fails behind a symmetric NAT, turn steps in as a relay. At the cost of routing all media through a server, ICE just orchestrates both, trying every path and picking the best. UPnP asks the router politely to open a port, and hole punching exploits the fact that two peers firing outbound at the same moment can meet in the middle, the foundation of WireGuard mesh tools like Tailscale. And once you've seen all those traversal gymnastics, it's worth stepping back and asking, was NAT really a good idea? The honest answer is it was a brilliant stopgap. It bought us 15 plus years of IPv4 runway, gave every home a free inbound firewall, hid internal topology, and let mobile carriers roll out 4G to billions without rationing addresses. But the cost was real. NAT quietly killed the end-to-end principle the internet was built on, broke protocols that embed IPs in their payload like FTP and SIP, forced P2P apps into elaborate workarounds, and at carrier-grade scale, it now shares a single public IP across thousands of subscribers, taking even the illusion of an address away from the user. With that honest accounting behind us, let's look at where NAT actually trips engineers up in the field. The classic one is forgetting to tag both interfaces, no IPNAT inside or IPNAT outside, and traffic just silently drops. Then there's the translation table filling up. Thousands of users behind one public IP eventually exhaust the 65,000 port range, so flows start failing at random. Asymmetric routing is another quiet killer. If the return path hits a different NAT router, there's no translation entry waiting, and the packet dies. Add in protocols that embed IPs inside their payload, where you need an application layer gateway to rewrite them, and UPnP, which cheerfully lets malware punch its own holes through your perimeter. And you've got the 5 pitfalls that show up again and again in real networks. So let's pull the whole story together. NAT exists because IPv4 ran out of room, and translating between RFC 1918 private space and public addresses bought us decades of breathing room. Static maps one-to-one, dynamic draws from a pool, but PAT is what you actually see everywhere. Many devices multiplex behind a single public IP using source ports, up to roughly 65,000 concurrent flows. Port forwarding and the stun, turn, and ICE traversal tricks exist precisely because NAT broke the original end-to-end model. IPv6 was supposed to retire all of this, and yet NAT is still everywhere. And that brings us to the cheat sheet, your quick reference for everything we've covered. Keep the 4 address terms straight. Inside local and inside global describe your internal host before and after translation, while outside global is just the public destination you're talking to. Below that, the 3 NAT flavors stack in order of efficiency: static, dynamic, and PAT, followed by the practical tools that let traffic come back the other way. Port forwarding for servers you control, and stun for peer-to-peer apps that need to discover themselves from the outside. And that wraps up our look at NAT. Next time, in Lesson 37, we shift gears into quality of service, the mechanisms that decide which packets get to go first when the pipe gets crowded. We'll unpack bandwidth, latency, and jitter and see how networks learn to favor the traffic that actually matters. Until then, thanks for following along, and I'll see you in the next lesson.